Hello everybody, I'm Luca Guidi, Jodoshi on Twitter and GitHub. This is my website, lucaguidi.com. Today I want to talk about Hanami API. Hanami is a full-stack web framework for Ruby, and Hanami API is the newest addition to the family. I'm the author of Hanami. It's a project that I started a few years ago. I'm in the core team of Trie. I'm the author of Reddit Store and contributed to a lot of popular Ruby open source libraries. I work remotely from Rome, Italy, as a top-tier backend architect. And let's get started with the Hanami API history. Why I decided to add this new component to the toolkit we provide. First thing first, I am with the team in the process of writing Hanami 2.0, and the old router, the 1.0 version, is based on a gem that is no longer maintained since a few years, so that is a liability. It was a liability for us, and so I decided to rewrite the router. And that first rewrite is the first alpha of 2.0 version. That worked well, but it had performance problems. I discovered after running in those benchmarks, after discovering a Twitter conversation, so that was casual. I didn't pay too much attention to the performance. I said, okay, I will optimize later, but then I discovered that the complete approach was wrong, and so make optimization on top of that code base would have been something really hard to achieve. So I said, okay, let's rewrite it with a proper way, and we will see what that means today. And then I got amazing performances. So I said, okay, how the entire community can benefit from the performance that this router can bring to people's apps. Usually speaking, when you are looking for a router, you are building something very low level, right? So I thought it's better to wrap it up into something that can provide a way to quickly build HTTP endpoint, APIs, and so on and so forth. So I created this small wrapper on top of the router, and that's how and why it was born, Hanami API. The other reason, however, given that it targets small HTTP endpoints, APIs, the risk of adopting a component from Hanami ecosystem is much lower if compared with Hanami, because Hanami is a full-stack web framework that is used to build full-fledged products, not just the HTTP part of it. So there is friction in the adoption, and here I just wanted to lower the entry level into the Hanami world. So those are the two reasons: performance for everybody and low risk of adoption. Now let's have a look at the syntax of it. It's very all here. It fits in this slide. So we have the require, we know it, and we have the app that inherits from Hanami API object. So it provides just one superclass that you inherit from. And you have at line 13 the classic syntax that you get from Hanami router. You have the HTTP verb, the path, the relative path, and then the endpoint. And the endpoint is everything that speaks rack. It means it can be an Hanami action, can be anything, a proc, anything that is compatible with the rack. Okay. The new addition here is what I call the block syntax, which is line 9 to 11. That means you still define the HTTP method, the path, and then instead of providing an endpoint, the endpoint is a block that you pass, and the returning value of this block is usually the body of the response. Okay, and this is clearly inspired by Sinatra. Now, other useful things. Line 14, mount a rake app. What that means, you have an existing rack app that you want to mount inside it, and you prefix with a path, in this case dashboard. So everything that starts with dashboard would be forwarded to this rack app, and then it would be up to this rack app to do to handle the request and return a response, of course. Another important, not important, but really cool feature is the scope. The scope acts as a prefix for the URL. That means any other route that is defined inside the scope would be prefixed with /API. But it's not just that. It gives the scope of execution for the rack middleware that are defined here. What that means, my authentication rack middleware that is declared at line 17 will be only used for the requests that are start with /API. Okay, and you can nest as much as scopes you want, and they will preserve the stack of the rack middlewares that you declared here. For instance, the other one that is line number 7 is used for all the incoming requests for all the routes because it's at the top, at the root level of the context. But again, because my authentication, line 17, is only inside this scope, then only the requests that are handled by this scope will use that authentication. This is useful, for instance, if you have versioning of your API and you want to use different middleware for different versions of your API. And then you run this app by instantiating it. And again, that's very it. The features fits on this slide. Params that you receive from the request, of course. Getter and setters for status, headers, body. Halting that stops the execution, redirect, JSON rendering, scopes that we have just seen, mounted apps, and rack middleware. That's very it on purpose because I wanted this to be very lightweight and performant. So let's talk about performance. I've after the first time that I wrote this router, that means the first alpha version of it, it was slow, I mentioned, right? And I used a benchmark written by Jeremy Evans, the author of Rhoda and the author of SQL, to compare how the new work was comparing with the other frameworks. And this benchmark is interesting. It does two things. One is it measures the memory footprint of an app. You have an app with 10,000 routes, and it says, okay, just booting it up, how much memory it takes. And if we see the results here, Rhoda is the winner here with 47 megabytes, and Hanami API is second just with 53 megabytes. And then you have, on the right side of this slide, you have Sinatra with 125 and Rails with 143 megabytes occupied, just booting an app with those frameworks with 10,000 routes. That's very it. And so this is important because the less memory you occupy, the better. It's more lightweight for your server, right? The other benchmark is the runtime benchmark. What that means is that you have the same app with the 10,000 routes, how much time it takes to complete the execution of 20,000 requests. All of those requests will hit the last route. This to measure the worst case scenario, right? And here there is no error in this slide. The problem with this slide is that Rails, Sinfield, and Sinatra are completing these in 17 seconds and Sinatra in 197 seconds, so they are outscaling the rest of it. If we just zoom in the left side of the previous slide, we see that Hanami API is the fastest one. It takes 1.11 seconds to complete, and RODA 0.34. So it's very, very fast on the runtime. Again, great performance was one of the reasons why I wanted to create Hanami API to make the power of the router available for everybody to have API apps just ready to be used, right? So the takeaway of this is not just the good numbers, is that competition is healthy for Ruby ecosystem. I've been pushed to do better because I've seen those benchmarks, and so I wanted to do better. And so if you believe that Rails and Sinatra are the two competitors here for full-fledged web apps and APIs, you may want to reconsider your position. So let's have a look at the implementation, how at the high level, how I managed to get these really, really fast. But before doing that, just a little bit of theory with emoji. So big O notation, what that means is a way to measure how a data structure perform a specific task. And so the concept here is that the time to complete it's sometimes tight, correlated with the size of your data structure. Let's give an example. An array, for instance, finding the last element of the array is the time to complete depends on the size of the array. If you have an array of 10 elements, then it would take, just inventing here, 1 second. If you have, I don't know, 100 elements, it will take 10 seconds, right? So it's tied to the size. It increases the time to complete. It grows linearly with the growth of your data structure, and that is O of n, which is at the bottom of this slide. The mid level here is logarithmic. Here I'm starting to decouple from the size of my data structure because I'm not going through all of the elements. My algorithm allows me to not evaluate all of them, just a few of them, some of them, and to get my result. Okay, and the other one is O01, which is constant time. It's amazing because it doesn't matter how big is my data structure, I will be able to get an element from it in just constant time. One example of it is a hash fetch from Ruby. It doesn't matter how big my hash is, fetch returns me an element in constant time. That is just great. So let's see a practical example. Guess who? I believe all of you are familiar with it. So imagine you need to find the character here that is on the right side of the screen, the blonde woman there, right? And with the O of n, let's say I have 24, yeah, probably, or 32, I don't know, characters. The thing here is that with O of n, let's say we are going one by one and saying, okay, this is not the character I'm looking for, this is not, and then because I'm looking at the last one, I go through all the elements, right? And the bigger the board, the game, the slower, the more time it would take me to get there. So again, it's not ideal. Logarithm, it's what we do when we start ask questions to the other person that is playing with us, to guess who. We start to ask, is the character a woman or a man? Is she blonde or not? Is she, I don't know, wears a hat or not? And that allows us, with this algorithm, allows us to not go through old characters, but just a few of them. And 001 is kind of cheating. We already know what's the character, so we are getting straight there to pick the character. So why I'm telling you this? Because the first improvement from the first alpha to the second one, which is the optimized one, was to change the data structure. And changing the data structure allowed me to change the algorithm and going from O of n, which is linear time, to O logarithmic with the logarithmic time in certain cases and constant time in other cases. So the first version was using an array to store all the routes, and so hitting the last one forced me to go through all 10,000 routes in the case of the benchmark, right? So that was slow by design. But changing the data structure, switching from an array to a trie, that helps to not to navigate this trie and not evaluate 10,000 routes, but just a subset of it. And again, previous version stored routes in a collection, and now it stores in a trie. Second enhancement, HTTP methods partitioning. What that means? Each partition has now its own trie. What that means? The first time that I switched from array to trie, it was just a gigantic trie with all the routes in it. But then I said, okay, if I make my data structure smaller, then I can get better results in terms of performance. And getting smaller data sets with a consistent partitioning, it's useful again to just reduce, to look at subset of what of the routes in my data structure. So I started to partition the routes, not just have a gigantic trie, but to have multiple tries partitioned by the HTTP method that they respond to. So there is a trie for get, trie for post request, and so on and so forth. So we have several tries inside here. So when I receive a get request, I just discard everything else and focus on this small box that you see on the screen. So that helped again with the performance for runtime lookup. But as I said, this is logarithmic time, this is partitioning. Let's have a look at how and if we can and how get 001 in certain cases. That means constant time to look up to a specific element. So we have fixed and variable paths, what they are. Let's start with fixed. Fixed are a string that starts with a slash and a word, okay? And it can contain multiple slashes for nested paths, but it's just as it is. The one with the variables, it contains a special character that starts with a semicolon, and it has a set of alphanumeric characters. That is a variable. That means at the runtime, I needed to interpolate that variable with what I receive from the actual path of the request. Let's give an example. I have this REST endpoint books/id. So when I receive /books/23, I can interpolate this ID with the actual value, and that will be part of the params. Okay, if compared with other things like just /book that is fixed, that is has its own performance advantages. So I started to create other partitions, one for fixed routes, again /book, and the other one for variable paths like books ID. Because books ID require runtime interpolation, regular expression matches, whereas fixed one are just give me this route, I know where to find exactly. Again, it's like a hash, right? You already have the key, you can get back what you're looking for, just asking the hash to do so. So they are stored separately, and so what I did is basically have the previous partitioning based on get, post, and all the HTTP methods. And here with these enhancement, we have only variables where you see get, post, and put. Okay, and the fixed paths are in a different bucket. Okay, and so by zooming in this fixed path, the last box here on the screen, inside of it, it has other buckets inside. So it sounds complicated, but if you look at the code here, it's very that simple. I have the fixed routes. They are partitioned by get, post, and so on and so forth. So you have a two-level hash, right? And what the code does at runtime invokes dig with the request method in the path that of the incoming request, and it returns an endpoint if there is one, or it returns nil. And so in the first case, the successful case, it's all on one. That's great performance time. Otherwise, it returns nil, and it proceeds with the interpolation algorithms. So to recap with the syntax, the first one goes into a fixed bucket because it's just slash dashboard without any variable. The second one goes into its own bucket because it contains a variable and it's a get request. And the third one, yet another bucket because it's a variable and it's a put request. So everything here, the takeaway of this section is basically if you are able to consistently partition your data set, then at the runtime when you need to find something, it's easier to look inside, I don't know, 10 routes rather than 10,000, right? Because you're able to combine all those partitioning, and so it just it looks to just a few candidates, and that is just great for performance. Another thing, microspeed enhancements. What that means is basically I measured each complex method in isolation. I basically try to write two versions of the same method and compare and benchmark the two implementations and pick the one that was faster, because this is the primary design goal was to make it very fast. Instance variables are faster than getters, usually speaking. If add foo is faster than unless foo nil, avoid each with object. Those are things that I usually use in other code bases where performance is not so critical, but here I wanted to avoid. My suggestion here is to always benchmark your code. Don't take these for granted. I personally use for this benchmark-bm gem, which is just great because it compares the two and gives you the difference between the two executions. So it's just great tool that I suggest to use. And again, benchmark your code. And the last principle, I just remove the dependencies. Usually there is this gem that's called Hanami -utils that is shared across all the Hanami gems. It provides, guess what, utilities. But this time I decided to not adopt it, and I decided to drop other dependencies. I implemented just a few functionalities from it, so I was able to not impose direct and indirect dependencies to the people, to the engineers that want to use a Hanami API. So the less code is loaded in memory, the faster for the boot time and for the memory footprint. So let's see if that was worth the effort here. So on before, this is the first, without the optimization, to complete this benchmark, it took more than 2 minutes, and it took basically more than 2 minutes to just run run the benchmark, and now it takes less than a second. If you see this 0.081, 81, which is just 81 milliseconds. The second benchmark is the 20,000 requests plus the startup time, and if you do the math, 138 less minus 131, it takes 7 seconds more or less to boot with 10,000 routes, and now it just takes 1 millisecond, 0.82 with minus 0.81, right? And the memory footprint before was 116 megabytes, and now it's just 73. Again, an app with 10,000 routes and time to complete 20,000 requests, hitting the last route. So I believe that this is a great candidate for you if you need to write an HTTP endpoint where performance is important, or if you want something very, very lightweight. I believe that the present of Ruby is bright and the future is exciting. Thank you very much.